Hello, we'll start within 2 to 3 minutes. I'm waiting for the participants. Hello, good morning, everyone. Today, I will discuss the frequency response analysis. It is very difficult to conduct the face-to-face lectures in the classroom, and also it is very difficult to you people to attend the lectures. So, if you have any doubt, then please raise your hand or put any message or any doubt in chat. Uh, because it is again very difficult to me and you people to interact one by one. So it is cover the some of the basic importance related to this unit number 4, that is a frequency response analysis. Under the frequency response analysis, the correlation between the time and frequency. Then we will see the basic concept of body diagram or body plot or logarithmic plot or the corner plot. And then under this body plot, we will see some of the frequency function factors. Then how to draw the magnitude plot and then phase body plot for each and every frequency function factors. Then we'll see the procedure to sketch the magnitude and then phase body plot. Then we'll see the phase margin and then gain margin, how we check the stability with the help of the GM and then PM. And then last bit of this unit is a Nyquist stability criteria. Okay. Here, the frequency response analysis. Frequency response analysis is nothing but the magnitude and then phase relationship between the sinusoidal input and then steady state output is known as a frequency response. The frequency response is studied or analyzed by keeping the amplitude of the input is constant for a variable range of the frequencies. The input, the canonical form of the system, that is G of S, is the forward path transfer function. H of S is the feedback path transfer function of the system. Then R of S is the input. C of S is the controlled output. And RT is in the time domain, equals this A into the sine of omega t. Then you have to study the output of the system, that is a frequency response. By keeping the amplitude is constant for a suitable range of the frequencies. And then C of t output, C of t equal to the B into the sine of omega t plus C phi. Okay. And then A is nothing but the input amplitude. After this input is applied to this forward path transfer function of the system, we get the steady state output of the system, that is the C of t equals the B into the sine of omega t plus phi. This part was already covered in the classroom on the 10th March 20. Then omega is the frequency, phi is the phase difference between the sinusoidal input and the sinusoidal output. Here, in case of the frequency response, we will consider the sinusoidal transfer function, the sinusoidal input, and then check the sinusoidal output with their magnitude and then phase. Then we see the correlationship between the time and the frequency response. That is the first bit, that is a correlation. Then correlation is a correlation between the time and the frequency. Correlation between the time and the frequency. That is a correlation means already studied in unit number 3, that is the time response analysis of the system, time response. And then consider some important design parameters such as delay time, rise time, peak time, settling time, peak overshoot, and then steady state error. Then in this chapter, we'll consider the standard form of the system. That is, the standard form of the system is, that is omega n square divided by s square plus twice zeta omega ns plus omega n square. And then consider the sinusoidal transfer function of the system as per the definition of the frequency response analysis, the relationship between the input and the output. And then you can calculate the magnitude and the phase. Then first, we converts the closed loop transfer function of the standard form into the sinusoidal transfer function of the system. The notes and then PPT already uploaded on the Moodle. Again, I have shared the second order system with their closed loop transfer function, that is omega n square divided by s square plus twice zeta omega ns plus omega n square. Then sinusoidal means replace s equal to the j omega. And then we can calculate its magnitude and then phase. Once you know the magnitude and then phase, then check the response of this magnitude against this normalized frequency, then phase against its normalized frequency, and then what will the effect of the zeta, that is a damping factor, because the damping factor is very, very important in case of the control system. Here the sinusoidal transfer function of the system is C of by R j omega equals the P of j omega, that is omega n square divided by j omega square, etc. That just only replace s is equal to the j omega in the given transfer functions. Then again, this is converts into the time constant form of the system. That is a time constant. That is 1 plus the ST1, 1 plus the ST2. In this way, converts into the time constant form of the system if you observe the PDF and then the equation 7.2, that is a T of j omega, by taking the omega n square common and converts into the form of 1 minus etc. That is a omega upon omega n square by zeta omega upon this omega n. Then put some values, because there are the two frequencies, that is the input frequency and then natural frequencies, and hence we consider for the simplicity that u equal to omega upon omega n is known as the normalized driving signal frequency. And then once you know the sinusoidal transfer function of the second order system is in the standard form, then converts into its magnitude and then phase. Why? Because we study after this, we study the Bode plot, and the Bode plot consists of the two plots. One is known as the magnitude against the frequency, and the second is known as the phase against the frequency. And hence converts this sinusoidal transfer function into its magnitude and then phase, or another term in the control system is known as the polar chord. Polar chord. And hence the magnitude equals 1 upon, here if you observe, the magnitude equals 1 upon under root real square plus the imaginary square. Similarly, the phase equal to, that is a minus. Why minus? Because the term in the denominator is 1 minus u square plus pi is zeta u, and hence here is a minus. Minus tan inverse imaginary part divided by this real, we get this phase. Then steady state output of the system for a sinusoidal input of the unit magnitude and variable frequency, that is a magnitude and then phase. Again, this magnitude and then phase used in the polar plot. Actually, polar plot is the prerequisite of the Bode plot, but not included in your syllabus. That is how to draw the polar plot. That is a magnitude against the phase, and check the clockwise and then counterclockwise in counternet, and then check the, with the help of this counterclockwise and clockwise, check the stability of system. Here the steady state output, that is a magnitude, that is a 1 upon, this is m, and this is a phase, that is a phase equal to the minus tan inverse by zeta u upon under root 1 minus u square. This is the C of t. Already at the beginning I said that is Rp is equal to the A into the U of t. Then C of t equals the B into the sine of omega t plus phi. That is a phi. Phi is nothing but the phase difference. This is nothing but the magnitude. And then with the help of these equations, we can comment on its magnitude and then phase, and then check the response of the magnitude against the normalized driving signal frequency. That is a normalized driving signal frequency is nothing but omega divided by this omega n. That is u equal to the 0, and this normalized frequency varies from the 0 to infinity plus infinity. That is u is equal to 0, magnitude is equal to 1, phase is equal to 0. That is a put the value of the u equal to the 0 into the equation 7.4. U is equal to 7, again put into this 7.4. U is equal to infinity, put into the equation 7.4. Similarly, the u is equal to 0, 1, infinity, or take the values between the 0 and infinity, and then calculate its magnitude, calculate its phase. Just for the simplicity, we have considered the u is equal to 0, 1, plus 1, infinity, and then calculated the values of the magnitude 1, 1 upon pi theta, 0, phase equal to the 0, minus 90, and minus pi, or this minus 180 degrees. And if you observe the response, this is the response. That is the magnitude, again the normalized driving signal frequency, that is omega divided by this omega n. Also the phase angle, that is a phi, equal to the minus tan inverse, that is a twice zeta upon under root 1 minus twice zeta square, again the normalized frequency. If you observe the magnitude, again this normalized driving signal frequencies for the values of the zeta is equal to the 0.707, as the magnitude u is equal to 0, magnitude is equal to 1, u is equal to infinity, magnitude is equal to 0. This is the response gets decreased, as the response of control system depends upon the value of the zeta. Value of the zeta lies between 0 to 1. If the value of the zeta is less than this 1 but greater than 0, if the value of the zeta is less than 0.707, then magnitude gets increased. If you observe the magnitude, this is the magnitude. That is the magnitude is inversely proportional to the value of the zeta. As the zeta decreases, magnitude increases. The same thing is happening in the response of the magnitude, again the normalized driving signal frequency. As the value of the zeta decreases, magnitude gets increases. Here again, if you want to take or using the MATLAB, it is possible to put the value of the zeta is equal to 0.2, 0.4, 0.6, 0.7, 0.9 and then 1, and then calculate its resonant peak, MR. This is MR is known as the resonant peak. If you consider this phase angle, again the u is equal to say 0, u is equal to 0, phase angle is equal to 0, u is increased from the 0 to this infinity, then again the phase angle is decreased from the 0 to this, here is a minus 180, that is 0 to minus 180 degrees. This is again, this is based on this phase angle minus tan inverse twice zeta u upon this 1 minus u square. That is a phase is depends upon the value of the zeta, that is a damping ratio or the damping factor. Here then again we'll why we study this magnitude and the phase, that is a correlation. With the help of this, we'll get some of these design specification, frequency design specifications, that is a normalized driving signal frequency, a resonant peak, then the bandwidth, again the phase margin, gain margin. That's what we starting from this standard of form, that is omega n square upon this a square plus twice zeta omega ns plus omega n square. Here if you observe again the frequency where m has a peak value is known as the resonant frequency. Here the frequency at u equal to the ur equal to the omega r upon this omega n. The magnitude is high, that is a maximum peak. This maximum peak is known as the resonant peak. Then how to derive this resonant peak? With the help of this equation. The frequency where m has a peak value is known as a resonant frequency, and then at this frequency the slope of the magnitude curve is 0. This equation is if you again try to recall in case of the time response analysis, again rise time, that is the time required to reach 100% of its final value, and the initial slope of the curve by taking the derivative, and the derivative is equal to 0. Same thing in case of the frequency response analysis. The frequency where m has a peak value and the slope of this magnitude curve is 0, let omega is equal to the omega r, then u is equal to say ur, u is equal to ur, omega is equal to say omega r. That is the dm by du at u is equal to ur equal to the 0. And if you simplify this equation, we will get this ur and then omega r. This is the time response specifications of the system. That is you already know U is known as the normalized driving signal frequency. At U is equal to UR, the slope of the magnitude curve is 0, and U is equal to UR equal to this 1 under root 1 upon under root 1 minus twice zeta square, or omega R is equal to the omega n into under root 1 minus twice zeta square. This is the frequency response specifications or the design parameters in the frequency response analysis. And then our heading is correlationship between the time and the frequency. We will see afterwards by solving the some equations. Omega R equal to omega n into under root 1 minus phi zeta square. Similarly, if you substitute this value of the UR at U is equal to UR, the maximum value of this magnitude known as a resonant peak. Resonant peak is nothing but the frequency at which the magnitude has a peak value is known as the resonant peak. At U is equal to UR, omega R is equal to omega n into under root 1 minus twice zeta square. We will get again substitute this value of UR for U. The maximum value of the magnitude is known as a resonant peak. This is the another frequency domain specification or design parameters in the frequency analysis. Omega R equal to 1 upon twice zeta under root 1 minus zeta square. And here omega R, if you observe that omega R equal to omega n into under root 1 minus twice zeta square. If you observe these two equations, already studied the omega d in case of the unit number 3, omega d equal to the omega n into under root 1 minus zeta square. In case of the time domain specification, mp, that is a peak overshoot, equal to e raised to exponential e raised to minus pi zeta upon under root 1 minus zeta square. Here in case of the frequency response analysis, mr equals the 1 upon twice zeta under root 1 minus zeta square. Similarly, calculate its phase, that is the phi r, that is a resonant frequency at U is equal to UR, or the UR equal to the omega n upon this omega r. Omega r. Then this minus tan inverse under root 1 minus twice zeta square upon this zeta. These are the frequency design specifications. Omega R, omega R, UR, MR. Then here for this feedback, this is again the depends upon this value of the zeta less than 1, or the value of the zeta lies between 0 to this 1, or calculate its bandwidth by considering the magnitude is less than or equal to this 0.707. For the feedback control system, the range of frequencies for which m is equal to or greater than 1 upon root 2. Already studied in case of this electronic circuit design or the analog circuit, how to calculate its bandwidth. The same principle is applied in case of this control system engineering. That is the frequency over the magnitude is equal to or greater than the 1 upon root 2. That is the 0.707. It defined as the bandwidth. Again, at bandwidth, this U is equal to UB equal to this omega B. That is the bandwidth, because the control system being the low pass filter at 0 frequency, magnitude is equal to say 1, and the bandwidth omega B is equal to the cutoff frequency. And if you observe, this is the again the magnitude, again these frequencies, M again this W, and here the bandwidth, the range of frequencies over which the magnitude is equal to or greater than this 0.707 is known as the bandwidth. This is known as a bandwidth. And here this bandwidth is compared with again this magnitude, that is magnitude is equal to or greater than this 1 upon root 2. And then again we'll derive this equation with the help of, you know, the magnitude already derived at the beginning of the second order systems. This bandwidth is equal to or the greater than this 1 upon root 2, that is a 0.707. Then u is equal to the ub is equal to this ur, and this ur already derived this equation, that is under root 1 minus twice zeta square. Put this 1 minus twice zeta square into this equation, we will get the bandwidth, that is ub equals this under root 1 minus twice zeta square plus again under root 2 minus 4 zeta square plus 4 zeta raised to 4. Then u is equal to, say, you know, again the equation already derived, that is omega r is equal to, say, omega n into under root 1 minus twice zeta square, that is 7.6 equation. Consider this 7.6 equation. Again the put u is equal to, say, ub into this equation, we will get this bandwidth, that is the range of frequency over which the magnitude is equal to or greater than this 0.707. Then our task is a correlation between the time and the frequency. Here, if you consider the step response of the system, the expression for the damped frequency already said, the omega d equal to omega n into under root 1 minus zeta square. Mp equal to e raised to minus pi zeta upon this under root 1 minus zeta square. This equation already derived in the unit number 3, that is a time response analysis. Then here, this normalized bandwidth, again this zeta, again this normalized bandwidth is equal to or greater than this 1 upon root 2. Then MR, that is a resonant peak. You know, this MR is nothing but the maximum peak at the resonant frequency. MR, the resonant peak of the frequency response. MP is the peak overshoot, that is the time required to reach its maximum peak at t is equal to Tp, is known as the MP, that is the peak overshoot of the step response for a second order system. And if you plot this MR MP against the value of the zeta, that is every parameter in the control system is related to the zeta. Thus, to design any control system, for the value of the zeta lies between 0 to 1. And hence, again, if you draw the response, that's MRMP, resonant peak. MR means resonant peak, MP means peak overshoot, again this value of the zeta. The comparison of the MRMP of this above, the two performance indices are correlated as both are functions of the same damping factor. Already said, that is MR and the MP both are against the value of the zeta, depends upon the value of the damping ratio only. It means that a system with a given value of MR of its frequency response must exhibit a corresponding value of MP if subjected to a step input. Subjected a step input means depends upon the value of the zeta. That is, both MR and the MP start decreasing as the value of the damping factor or the damping ratio gets increased from the 0 till up to this 1. For the value of the zeta greater than 1 upon root, the resonant peak MR, that is resonant, does not exist and the correlation breaks down. Why? Because the control system is designed for the value of the damping factor lies between the 0 to 1 for the stable system, and hence don't consider the value of the zeta greater than this 1 upon root 2. And then for zeta greater, the step response oscillations are well damped and the MP is hardly predictable. This is again the omega r upon this omega d. Omega d is nothing but the damped oscillator frequency derived in case of the time response analysis. Omega r is nothing but the resonant frequency And here the correlation between the omega r and the omega d. That is the omega r already derived in the above slides. Here omega d already derived in case of the time response analysis. If we take the ratios, that is omega r upon this omega d, that is a correlationship between the time and the frequency. That is ratio of these two expression is which is also function of the zeta. If you take the ratios of these both the frequencies, that is the resonant frequencies and then damping frequencies, again both these ratios is depends upon the value of the zeta. That is this is the value of the zeta. The ratio gets decreased as the value of the zeta increases from the 0 to 1. But this is the maximum equal to this 0.707. Otherwise, the system is said to be unstable. Here, this is the correlationship. Similarly, it is possible to obtain the relationship between the MR and the MP by MR is nothing but the resonant peak, MP is nothing but the peak overshoot, and then take the ratios, we will get the relationship. And this is about the first bit, that is a correlation between the time and the frequency. Means derive the equation of the omega r, derive the equation of this MR, derive the equation of the normalized driving signal frequency. These are the design specifications in the frequency domain. Okay. Then some other design specifications are the design parameters used in the frequency response analysis we'll see in the Bode plot. Here the Bode plot. First, today we'll see only the basic frequency function factors of the Bode plot, and then how to draw the magnitude Bode plot and then phase Bode plot for the frequency function factors. Okay. Here the hello. Hello. All other participants, you have received the audio. Hello.
Yes, sir.
Hello. All of you received the audio.
Yes, sir.
Yes.
Okay.
Yes, sir.
Okay. Okay. I will continue. Hello. Hello. Today we will see some of the basic part or this basic logic of the Bode plots. These some of the students they have completed the diploma. They know the basic logic of the Bode plot, but most of the students are not getting how to draw the Bode plot, because I have uploaded the some of the images of the book, that is Anand Kumar. But today we'll see today and then tomorrow I will teach to you people how to draw the Bode plot, magnitude Bode plot, and then phase Bode plot. Bode plot is known as the logarithm plot. It is also known as the corner plot. Why this is called as a logarithmic plot? Because in case of this Bode, that is this is actually the name of the scientist, name of the researchers, that is H.W. Bode. And he has developed the magnitude Bode plot and then phase Bode plot to check the stability of a control system in the frequency domain. Then at the time of checking the stability in the frequency domain, has considered he has considered the open loop transfer function of the system. That is, all of you are aware the open loop transfer function. That is a G of S and then H of S, GSHS is known as the open loop transfer function of the system. Then consider the sinusoidal transfer function of the system. Already I said at the beginning of the correlation, consider the transfer function, then calculate the or converts into the sinusoidal form. That is just replace S is equal to the j omega. S is equal to the j omega is in the given transfer function. Okay. Then converts the sinusoidal transfer function is into the time constant form. That is a time constant form. That is a 1 plus in the numerator and then 1 plus is in the denominator. That is a 1 plus and then in the numerator and then denominator is nothing but here if you consider the transfer function, that is a 1 plus, that is a 1 plus ST1 or this STA, that is a ST1 divided by this again 1 plus STB or any other notations you can refer. That is STA, STB, etc. That is a 1 plus ST1. Again this 1 plus STA. Here is a multiplying gain factor is again the K. Here in denominator again S raised to N. That is a S raised to N. That is N. That is an integral term. K is a multiplying gain factor. This is known as a time constant form. That is a in the real form. That is a time constant form 1 plus ST1. Or here sometimes there may be a complex conjugate zeros, that is S square plus twice zeta omega ns plus omega n square, or 1 plus BC plus AC square, 1 plus here is a BC plus AC square, BC plus AC square. This is nothing but a complex conjugate, sorry, CA square. Here is the similarly, it is very difficult to write down the test. That is a 1 plus the BC plus CA square. That is a complex conjugate zeros and then complex conjugate poles. Here this is this term is known as a time constant form. That is the first